Hi, I'm Dan Zanoble, and this is my submission for the ENPM701 final challenge. The goal of this assignment was to program the robot to autonomously pick up and deliver 9 colored blocks to the construction zone in the correct color order: red, green, blue. The blocks must be delivered in 10 minutes, and any contact with the walls would be an instant DQ. Any blocks that are knocked over are not counted. Scoring is based on how many blocks are delivered. The robot begins in the 2 by 2 foot landing zone, and the blocks must be delivered to the 4 by 4 foot construction zone. The blocks can be randomly placed anywhere within the rest of the 10 by 10 foot map. I had 2 practice runs and 2 final attempts to complete this challenge. The main body of the robot is a DF Robot bearing kit. 4 DC motors powered by 5 AA batteries drive the wheels and steer using differential drive. A servo-driven parallel gripper is mounted on the front. The sensor suite consists of a Raspberry Pi camera, ultrasonic distance sensor, an IMU for tracking rotation, and encoders on the back right and front left wheels for tracking wheel rotations. The IMU is hooked up to an Arduino Nano to make use of the Adafruit libraries. The brain of the robot is the Raspberry Pi 4, powered by a rechargeable power bank mounted on the back of the robot. The dual H bridge was used to control whether the right or left wheels received power from the batteries and which direction the current would flow to drive the wheel backwards or forwards. I designed and 3D printed my own custom mounts for the camera, the ultrasonic sensor, power bank, and Raspberry Pi. The mount for the Pi incorporated a little Raspberry Pi case that I already had. I decided I wanted to mount the battery vertically early on to leave additional space to mount the rest of the hardware. My initial approach to this challenge was to attempt to incorporate all of the robotic capabilities I had learned throughout this class, and some topics I've learned in other classes. The bedrock of my program was accurately tracking the present location of the robot. To do this, I initiated a robot position list containing x, y, and theta for its position and angle. I created a serial thread that would continuously read data from the IMU and update the robot's angle accordingly. I created movement functions that would move the robot forwards or backwards by an input distance, move the robot to a specified XY position, or move the robot a specified distance away from the wall using the ultrasonic sensor. All of these functions used the encoder and IMU data to continuously update the robot's XY position. The IMU data was also fed into a proportional controller to keep the robot moving straight. I also created an ultrasonic sensor ping function that was used to reestablish the current position of the robot after every block was delivered, to reduce error introduced over time. I used HSV masking and contour detection to place bounding rectangles around the blocks. From the position and height of the bounding rectangle, I estimated the angle and distance to the blocks. This distance estimation was calibrated by taking images in the challenge arena. By fitting a power equation to the data, I obtained this equation. Based on the current position of the robot and the distance and angle of each block, the XY position of each block on the map could be roughly determined. I created a serial thread for the block tracker that continuously estimated the position of any block within view and added this data to a block location tracker. If a block was sighted that was estimated within a certain distance of a known block position, it was averaged with that reading. Otherwise, a new block position entry was created. Block positions were updated whenever the robot conducted a visual sweep of the map, and the updater was turned off when it was time to grab a block. Once all the block positions were known, an A-star path planning algorithm was used to find a path to a given location while avoiding any blocks. Once the target block was identified, the robot planned a path to it and used the move to XY position function to move to each waypoint along the path. When it was close enough to the block, it would use visual data only to align and move forward until it could grip the block. On doing so, it used A-star to path plan and navigate back to the drop-off point, dropped off the block, then re-established its XY position with the ultrasonic sensor. The robot then conducted another visual sweep of the field to update the block positions, and continued the cycle until all blocks were retrieved. Testing in my apartment showed that this approach was robust and would successfully deliver at least 3 blocks. Both trial run attempts failed to retrieve even a single block. During the first run, the block detection failed to identify any blocks. The second attempt failed when the ultrasonic sensor inaccurately read its distance from the wall as much closer than it really was, preventing it from accurately path planning to the target block. Additional testing showed that the ultrasonic sensor had a timeout issue, where it would wait forever if it failed to hear an echo, freezing the robot in place. To solve the issue of block detection, I added a command to turn off the automatic white balance adjustment a few seconds after the camera starts up, and ensured it was pointing at a white object on startup. This allowed me to track blocks much more consistently in different lightings, which was critical when practicing at home. I took videos on the actual challenge arena after turning off white balance and ensured that my updated HSV and shape filtering would identify blocks from up to 6 feet away without introducing other artifacts. To save time and reduce reliance on the shaky block position estimation, I removed the A-star path planning and the continuous tracking of block positions. Instead, I used horizon detection methods to find a triangle shape representing the straight line path of the robot plus a buffer zone. The robot would turn until a block of the target color was in the path, and blocks of no other color were in that path. If two blocks of the same color were in the same path, it would target the closer one. If it failed to find a viable path, it would turn to find a clear path, move diagonally, and then attempt the search again. This would continue until it found a viable path. This way, even if a block was really far away, it would still eventually be seen and targeted. This would prevent the issue I experienced in my first practice run. I solved the problem of missing an echo and then waiting forever by introducing a timeout. If it waits a certain amount of time to hear the return, it just acts like it heard it anyway and returns a very large distance value. I filtered out these and other extreme outliers by taking 20 samples for each distance measurement and taking the median value only. Testing at home showed the sonar could now be used reliably to position the robot 100 plus or minus 5 centimeters from a given wall. This would prevent the issue I experienced in my second practice run. Testing the updated code showed the robot could consistently deliver at least 3 blocks to the construction zone, as shown here. Satisfied with the routine I had created, I was excited to see it in action during the final challenge. I looked forward to seeing the payoff for all of the skills I'd learned over the semester, including Raspberry Pi setup and operation, object detection and tracking, servo control with PWM, locomotion and kinematics, localization, and robot perception and path planning from my 2 other courses this semester. The 30 or so hours I'd spent putting this all together would all be worth it, because I knew I had a robust program that would successfully deliver all 9 of the blocks. My first run failed to deliver even a single block. While trying to position itself 100 centimeters from each wall, the ultrasonic sensor returned a distance of 90-something centimeters, no matter how far away it actually was. This demonstrated that, for the purposes of this competition, the ultrasonic sensor was utterly worthless, and all reliance on it would have to be completely removed from my routine for the second run. I decided to put my faith in the encoders and IMU only to keep track of the robot's position. My second and final run failed to deliver even a single block. It was programmed to go for the closest red block in sight, and the 2 blocks were exactly the same distance away, so it became paralyzed with indecision, uselessly oscillating back and forth between the 2 target blocks with no hope of recovery. As I watched it tick back and forth, it was like I could see it ticking away the hours of my life I had spent on this project. With each turn, I envisioned my score on this assignment dropping, until the full 10% of my final grade that this challenge was worth had completely evaporated into nothing. Why am I here? I thought. Why are any of us here? Are we here just to suffer? Why do we strive to accomplish anything, when it can all be taken away by something as simple as 2 blocks coincidentally being the same distance away? The pride I had felt in my work slowly drained out of me, until nothing remained but a dull, throbbing anger, made worse by the fact that it could only be directed at the vague concept of, well, I guess I should have thought of that. Here's the wisdom I would pass on to anyone else taking this class. Number 1, Murphy's Law. Anything that can go wrong will go wrong. Prepare for every single eventuality. If you feel confident your routine will work, you haven't thought of everything yet. This applies to full-time work too. As an engineer, you should always be challenging your assumptions and looking for ways that things can go wrong. Number 2, just because it works at home doesn't mean anything. If you haven't tested it in the challenge arena, you haven't tested it, period. Utilize every single nanosecond you have in that lab to test things. In the working world, this translates to making sure your test environment matches your applications as much as possible, and be prepared to adjust for the things that don't match. Number 3, have fun. Despite how I made it sound at the end there, this class is actually awesome, and if you just do all the homeworks, you'll be fine even if you fail the final challenge. Hands-on experience like this is the best way to learn how to solve real-world problems, and Dr. Mitchell does a great job breaking it up into digestible chunks with each homework assignment. The content in this class can be applied to a ton of projects, both professionally and for fun. You get to keep the robot, so you can be sure I'm going to program this thing to get me a beer or something. Thanks, Dr. Mitchell.